Thank you very much, Danuta, for the introduction, and thank you as well to Pedro, Rebecca, and Gianni for inviting me to speak. Our group is a relative newcomer to the field cycling world, having only got our machine about 3 years ago. So it's really nice to be invited here to share some of the research that we've been doing in Cambridge and doing in collaboration with Professor Jean-Pierre Courbe. So, as Danuta suggested, I'll start by telling you a little bit about heterogeneous catalysis and how we can study it with high field relaxation. Then I'll discuss the need for field cycling and the information we can get about single and multi-component adsorption. So heterogeneous catalysis covers any form of catalysis where the catalyst and reagents are in different phases. And most commonly, it's carried out with a solid catalyst and liquid or gaseous reagents. And this is a huge industry, contributing more than £50 billion a year to the UK economy alone. And it's also a really interesting scientific problem, requiring understanding over a range of different length and timescales, from bed scale flow patterns and product distributions, down to molecular scale adsorption and understanding which species are actually reaching the catalyst surface and reacting. And it's this latter category of adsorption that I'll focus on today, as over the years we've found NMR Relaxometry to be a really effective tool for probing adsorption. So, as a quick introduction to the materials, there's a huge range of heterogeneous catalysts out there, including supported acid-base catalysts like the sulfonic acid on the left, precious metal or transition metal supported catalysts like those in the middle, and even zeolites on the right, where the pore size is comparable to the size of a molecule. So you get all sorts of interesting shape selectivity effects. And in this talk, I'll focus more on metal-supported catalysts, which typically have high surface areas, up to hundreds of meters squared per gram, leading to high metal dispersions and high catalytic activities. And they also have quite large porosities and nanoporous networks, with many being mesoporous, which means they have pore sizes between sort of 2 and 50 nanometers. These materials can contain paramagnetic or ferromagnetic species, either as active catalyst metals, as promoters, or as low-level contaminants from the synthesis process. And they also have highly polar surfaces and often have high surface hydroxyl densities, which leads to very strong interactions at the surface. So, given all that information, when you fill a mesoporous heterogeneous catalyst with liquid, you'd expect to see 2 relaxation times. A short T1 for molecules at the surface, which experience strong binding sites and the effects of any magnetic metals present, and a long T1 for molecules in the bulk pore space that are far away from the surface. But since this is a dynamic system, exchange between the surface and bulk layers averages these contributions. And according to the 2-phase fast exchange expression, as shown, where P is the surface population fraction and the TS and TB refer to the surface and bulk relaxation times respectively, we actually only see one averaged environment. And this one time constant contains a lot of detailed information about the catalyst pore size, its geometry, the chemical composition of it, the adsorption strength. And it's actually very hard to interpret all of this information from a single measurement. So what we often do at high field strength is take the ratio of T1 over T2. And for these mesoporous catalyst systems, the surface relaxation time constants are normally quite short, on the order of microseconds to milliseconds. The population term can actually be quite high, population fraction even, so it's between 0.01 and 0.3 are quite common, and the bulk relaxation times are long. And that means that we can approximate our observed measurement as being equal to P times 1 over the surface relaxation time constant. Then, taking the ratio of T1 over T2 cancels out this population term, and you're left with a metric defining molecular mobility that is, to a decent approximation, independent of pore size, independent of things like paramagnetic concentration, and ranges from 1 to a few hundred, allowing a good discrimination of different adsorbates. And how this ratio relates to the adsorption strength can be seen in the figure on the right. For fast motions, the T1, T2 ratio tends to 1, as is often seen for bulk liquids. As the adsorption strength increases, the motional correlation times increase, and the T1 and T2 values start to diverge, which means that a larger T1, T2 ratio is indicative of a stronger surface interaction. So, for clarity, for the purposes of this talk, I've presented that argument based on a very simplistic model, i.e. BPP theory. But this relationship between T1 and T2, or T1 over T2, and interaction strength holds for other modelling approaches more focused towards the study of liquids in porous media, and it's also supported by a wealth of experimental evidence. As a couple of examples of it working very nicely, the graph on the left shows a relaxation ratio approach for estimating interaction strength. And this is compared to the desorption energy obtained from temperature programmed desorption, or TPD, for water in a range of porous catalyst supports. And you see there's a really nice agreement between the two techniques. And then on the right-hand side, the oxidation of butane diol in a methanol solvent was carried out over a range of different porous catalysts. Taking the T1, T2 ratio of the reactant and dividing it by that of the solvent showed a really strong trend between the relaxation measurements and the reaction conversion, with higher values of this beta parameter, meaning a greater surface accessibility of the reactant. So here we're getting competitive adsorption information relevant to catalysis straight from the relaxation data. Of course, there are limits to analysing the T1, T2 ratio in this quite phenomenological manner. So one limit might be that our assumption that the bulk contribution is negligible is not always true. For weakly interacting species or larger porous media, this might not be the case. And the dependence of T1 on T2 on the population becomes far more complex. A second example could be when multiple relaxation mechanisms are occurring concurrently. And one that we commonly see is for liquids in porous media, where the effects of internal gradients can be quite strong. So since the magnetic susceptibility of the porous matrix is different to the magnetic susceptibility of the liquids inside the pores, when we put this sample in a magnet, a gradient is established at the pore surface. And this magnetic gradient causes additional T2 relaxation and increases the value of T1 over T2 without changing the interaction strength. And this is shown on the right-hand side for the T1, T2 experiment of cyclohexane in a platinum titania catalyst, where the effect of internal gradients is particularly evident from this stretching that we see in the T2 domain. But it's not always that easy to spot it. So in situations where a single point of high field information isn't enough to fully understand the adsorption behavior, field cycling approaches can be used to obtain a much more detailed understanding of what's going on. The timescales of motion we probe with NMR are inversely proportional to the frequency of the relaxation experiment. So on high field spectrometers, like those on the right-hand side, we're only getting a single point of information about relatively fast molecular motions. When we carry out field cycling measurements using conventional stellar type FFCs or Zulf type setups, we obtain the relaxation behavior over a wide range of frequencies, and hence over a wide range of timescales of motion. And what's particularly important for these porous media samples, these porous catalyst samples, is that with field cycling, we can access these low frequency measurements and obtain information about slow molecular processes that can only really be associated with surface diffusion type measurements, surface diffusion type mechanisms. And this is what we'll focus on in order to better understand the adsorption processes that are occurring. So for this audience, I won't go through the field cycling technique, as I'm sure you've all seen it many times before, but I will reiterate what I said on the previous slide, that this technique allows us to probe relaxation at very low frequencies and hence very long timescales of motion. For the rest of this talk, I'm going to focus on a case study of not just water, but a wide range of different liquids imbibed within γ-alumina. And I'll show you how we've used the relaxation methods that I've just discussed to understand what's going on with the adsorption. So γ-alumina is a typical catalyst support material, and it can be used as an acid-base catalyst in its own right. We ran some characterization on the batch of alumina I'll talk about, and it's shown on the left-hand side along with a picture of the alumina itself. We found it had a high surface area, a reasonably high pore volume, had a monomodal pore size distribution centered about 9 nanometers, and it contained a small but non-negligible concentration of paramagnetic Fe3 impurities according to ESR. And for the measurements, the NMR measurements that I'll present, each alumina sample was dried prior to imbibition, and the extra pellet fluid was removed before analysis. So we're really just measuring the liquid that's directly inside these alumina pellets. And to start off with, here's the data we get for doing this conventional high field T1, T2 approach. And I've taken a bunch of different liquids imbibed in γ-alumina, and I've plotted their T1, T2 ratio against the relative polarity, which we're using for this polar alumina as an analog for interaction strength. And on first sight, it's not too bad. So we've got the general trend that the more polar liquids show higher T1, T2 ratios. The less polar liquids, like the alkanes, show smaller T1, T2 ratios. But the more you look at the data, the more oddities and conflicting bits of information there are. So, for example, we're predicting that heptane is actually much more strongly interacting than cyclohexane and toluene. Acetone is very weakly interacting. And DMSO and methanol, despite being very different in terms of their polarity, are apparently quite similar in terms of their interaction strength. So there's not a huge amount of discrimination here, and we need more information to really understand what's going on with the adsorption process. So this is where we turn to fast field cycling. We started off by looking at the relaxation behavior of 8 bulk liquids, and these 8 liquids will form the basis of the study. So despite being very different in terms of their viscosities, their intermolecular interactions, and generally most physical properties, the NMRD profiles of all of these liquids were very similar. There was one high frequency feature indicative of fast translational processes in the presence of dissolved oxygen. And then after that, they plateaued off, and from about 10 megahertz down to 10 kilohertz, the profiles were very flat. And none of these profiles went above an R1 value, which is 1 over T1 of 1 per second. So really small numbers. However, if you take these same liquids and you imbibe them in those γ-alumina pellets we were talking about, there's actually a huge range of relaxation behavior. And that goes from down at the bottom, these non-polar species like heptane, cyclohexane, and toluene. They show fairly flat profiles, a sort of logarithmic dependence of the relaxation rate on the frequency. And even at 10 kilohertz, they're not exceeding relaxation rates of about 1 to 3 per second. That's similar behavior for acetone. And then if you look at some of the more polar species like DMSO, THF, and methanol, you get much steeper profiles. And these show power law frequency dependencies. They're reaching relaxation rates of about 100 per second, or 20 to 100 per second at low fields, and are very different in terms of their profile to the non-polar species. And then finally, water it's got an even larger relaxation rate, and it's got much more featuring in its NMRD profile. So what's interesting is because we've done this all on the same γ-alumina, the same support, if we have a look at the low field relaxation behavior, we can use that as an estimate of the interaction strength. And we see that already we're getting a much more sensible ordering in terms of the relaxation rate that we did from the T1, T2 data. The only exceptions being that acetone is quite weakly interacting here, and toluene is perhaps a bit more weakly interacting than we'd expect. And we'll come back to explaining why that is or getting a more robust ordering of interaction strength when we talk about modeling of these systems in a bit. But first, we thought we'd take a closer look at the T1 relaxation data at each field strength. And we performed an inverse Laplace transformation to get the T1 distributions of each liquid. And here I show a comparison of the T1 distributions for each of the liquids at one field strength. And you can see that most of these are nice, neat, single component relaxation distributions. But for acetone and for methanol, there's actually a second component, a second very well-defined component in these profiles. And this is consistent across the frequency range. We keep getting this second component. And that's indicative of a second dynamic environment. There's something else going on with these systems. You could hazard a guess at the sort of things it might be, but we thought we'd approach this with a few more experiments to really get a handle on what this second environment is and what it's telling us about the adsorption process. So for methanol, you've got two very different functionalities. You've got the aprotic alkyl group, can't exchange, and you've got the protic hydroxyl group that can exchange and will be directly involved in hydrogen bonding. So it's reasonable to assume that these two environments might differ in terms of their relaxation behavior. And on the left is the T1 distributions as a function of frequency for normal methanol, CH3OH. And at the bottom is the NMRD profile split out into this fast and slow relaxing component. Now, unfortunately, with field cycling, with fast field cycling, you're not able to get chemical resolution. So in order to assign these peaks, what we did was we repeated these experiments with some partially deuterated analogues of methanol. So we took CH3OD, we imbibed that in γ-alumina, looked at the profiles, and we had completely eliminated this fast relaxation component. We were just left with the slow one, and this was pretty good evidence that that slow relaxation component could be assigned to the alkyl group. Then we did the same with CD3OH, and we found that this fast relaxation environment was associated with the hydroxyl group of methanol. And we'll come back to the difference in this relaxation behavior and why they're different when we talk about the modeling shortly. Now, for acetone, unfortunately, the two environments are chemically equivalent. So the same explanation doesn't work. And a further oddity is that DMSO, which is structurally quite similar to acetone, shows a completely different NMRD profile. Acetone looks very weakly interacting, DMSO looks very strongly interacting. And the reason for this, we thought, was actually due to the acid-base nature of γ-alumina. So even at room temperature and pressure, people have seen that when you put acetone in γ-alumina, you get this aldol condensation shown at the bottom. And the acetone reacts to form an enolate and a beta hydroxyketone intermediate, B and C respectively in the diagram, before dehydrating to make a mesotyl oxide product. So what we thought was going on was that the reactive acetone was forming one of these intermediates, and these more polar intermediates were outcompeting acetone for surface binding sites and making the interaction strength of acetone with the surface much, much weaker. Now, obviously it's a bit of a stretch to conclude this just from the NMRD profiles. So we did some carbon-13 NMR of acetone imbibed within γ-alumina, and we got clear resonances that could be ascribed to this beta hydroxyketone intermediate and the mesotyl oxide product, so C and D respectively. And this gave us good confidence that this is what was going on, and it was this competitive adsorption process that was making acetone appear, well, in fact, making acetone be so weakly interacting. So now that we've got a good handle on what the data are telling us, the next step would be to fit the data with an appropriate relaxation model and to robustly rank the interaction strength of these adsorbates. But for liquids in porous media, this is quite a complex task, as there's lots of different interactions going on and modes of motion that may contribute to the observed relaxation behavior. And this means that many different relaxation models coexist in the literature, and they've been applied to very similar porous systems to the one that we're studying. So how do you go about identifying the most dominant interactions and modeling them? Well, you can look at the material characterization. So one important thing here is that we have a small but non-negligible quantity of paramagnetic impurities. So they may be important, as these are very powerful relaxation sources. You can look at the expected solid-liquid interactions, which here, depending on the adsorbate, vary from van der Waals forces to really strong and directional hydrogen bonding. You can look at the shape of the profiles, which again are varying for us massively. And if after that you can't come up with a good option of what you think is dominating your relaxation behavior, then you can do more experiments. So variable temperature or deuterium experiments. And that's exactly what we did for this system. So we took a subsection of the liquids that I've already shown and ran variable temperature fast field cycling measurements between about 5 and 125 degrees C, limited by the melting and boiling points of these solvents or these liquids. And you see some really interesting trends that can help us classify these adsorbates into groups as non-polar, polar aprotic, and polar protic, where here I'm using aprotic to describe something that can't exchange hydrogens and protic to something that can exchange hydrogens. So in the top left, the non-polar cyclohexane shows a decrease in the value of R1 with increasing temperature at all field strengths. That's similar to the behavior you'd expect to see from a bulk liquid. For polar aprotic species like THF, DMSO, and the CH3 group, the alkyl group of methanol, the same decrease in R1 with increasing temperature was observed at high field strengths, but this began to plateau off at high temperatures and low field strengths. I suppose that's most clearly seen here in this DMSO data, where everything's starting to converge at low field strengths. And then finally, for the polar protic species, an inversion of the temperature-dependent relaxation behavior was observed. So we get this same trend of the R1 values decreasing with increasing temperature at high field strengths. But at low field strengths, the R1 values actually increased with increasing field strength. And this behavior has previously been seen for protic liquids undergoing exchange at the pore surface. And the negative activation energy at low field strengths derives from the difference between the true activation energy of diffusion and the surface adsorption energy. I suppose it's worth noting, sorry about that. I suppose it's worth noting at this point that the methanol OH group is quite noisy in terms of the data. That's because it comes from a 2-component fit, whereas all of the others were just a single component fit. And the OH behavior is quite sensitive to noise, more so than CH3, because it's the minor environment, which means that it's not particularly clear to see this inversion in the hydroxyl group of methanol. But I hope you'd agree that the methanol OH data looks much more similar to that of water than it does to the CH3 group of methanol. And then just as a slightly different way of visualizing that data, we've put it into an Arrhenius representation. And you see these same trends of the non-polar species, cyclohexane, showing linear relaxation, linear Arrhenius behavior, normal Arrhenius behavior, the THF, DMSO, and methanol, these polar aprotic liquids, show this leveling off. And methanol and water start to show this inversion. So now we can start putting together all of this information that we have and that we've built up and identify the most relevant spin interactions leading to relaxation. So for the non-polar species, we remember there's a small amount of paramagnetic impurities present. Interactions between the adsorbate and surface are weak, as indicated by the fairly flat NMRD profiles. A normal temperature dependence was also observed, and this is all consistent with relaxation dominated by a surface diffusion mechanism in the presence of paramagnetic species. And this is shown schematically in the figure on the left, where a molecule hops between binding sites with a characteristic hopping time tau m before desorbing and leaving the surface with a characteristic desorption time tau s. And we modeled this behavior with a Korb type expression and included a Lorentzian function to capture the fast motions occurring at high field strengths. And from this fitting, we were able to extract surface hopping times, tau m, which can be converted into a surface diffusion coefficient using the expression there. And by comparing these surface diffusion coefficients to the bulk diffusion coefficients, it was possible to rank the interaction strength of each adsorbate as toluene being more strongly interacting than cyclohexane, which is about the same strength as N-heptane. And this is great because this ordering is consistent with what we'd expect based on the physical chemistry of the system. So toluene has additional pi-type interactions, which give it a slightly stronger interaction with polar surfaces than you would expect for alkanes, which are largely just van der Waals type interactions. And when people have done competitive adsorption studies of toluene and alkanes in similar silica systems, they found that toluene was able to consistently outcompete the alkanes for surface binding sites. So not only has this given us a really nice and really consistent order of interaction strength, there's also one other thing that I'd highlight, which is if we were to do this simple analysis where we just looked at the relaxation rates and just use the relaxation rate at very low fields to rank our adsorbates, we'd get a slightly different ordering of interaction strength. And this really shows how treating the data holistically and going through with this modeling approach gives you the most robust ranking of interaction strength that we can get. For the polar aprotic liquids, the NMRD profiles are much steeper than those of the non-polar liquids, indicating a stronger interaction with the surface. Now, hydrogen bonding will impose a directionality on the surface binding, and it'll hold these 1H spins away from the paramagnetic impurities. Combining this information with the very weak temperature dependence at low field strengths that we saw, it appeared that actually this relaxation behavior was different, and it was more consistent with an intermolecular pathway where the molecule binds to the surface for an average duration tau A before dissolving into the bulk. The molecule then explores the surface through a series of binding events separated by bulk excursions, and the strong directionality of the binding leads to a slow loss of correlation. And we modeled this using an intermittent model, and again a Lorentzian expression to capture the fast motions. And we got excellent fits and could use, the expression. It got excellent fits and we could use the values of this adsorption time tau A to rank the interaction strengths. Unfortunately for our data, the values of this prefactor, A intermittent, and tau A were somewhat correlated. So for us, the most robust results were obtained by looking at the product of these two numbers. And this allowed a ranking of methanol being more strongly interacting than DMSO, which was more strongly interacting with THF. And again, this is an ordering that is perfectly consistent with the polarity of these molecules and agrees with competitive adsorption studies that have been done with methanol and THF in polar catalyst materials. Now, finally, for the protic liquids, a number of interesting features are visible. So we've got a power law frequency dependence in the NMRD profile, a plateau at low frequencies that's not there for any of the other liquids, and a local relaxation enhancement at about 1 megahertz, which is a telltale sign for paramagnetic type relaxation. And furthermore, you can renormalize all of these protic NMRD profiles to form a single master curve, as shown on the insert on the left-hand side. And this is strong evidence that they're all actually relaxing via the same mechanism. And the unique relaxation behavior of the protic functionality was further confirmed by the temperature-dependent relaxation behavior of deuterated methanol at low field strengths. So I repeated some of those experiments I showed earlier, and here I've just got the data at 10 kilohertz to show the temperature-dependent relaxation behavior of CH3OD, so just the alkyl group, and CD3OH, just the hydroxyl group of methanol. And here we clearly see that the alkyl and hydroxyl functionalities are not relaxing via the same mechanism. They've got completely different temperature dependencies. And It's the exchange of the hydroxyl group within the hydrogen bond network at the pore surface that's causing these two to differ. And that might be with surface hydroxyl groups directly or strongly bound chem-adsorbed water. But putting all this together, the data seem to be most consistent with a surface diffusion mechanism in the presence of paramagnetic species. And this diffusional process is similar to what we saw for the non-polar species, but the exchange greatly increases the effectiveness of the relaxation, and the ordered hydrogen bond network controls the geometry of this diffusional process. So we captured these effects using the analytical model shown here, which describes relaxation caused by proton diffusion in the presence of paramagnetic species. And the renormalized NMRD profiles showed an excellent agreement in terms of the correlation times and the apparent power law, or chi. So in this case, we aren't able to actually separate out the interaction strength of water and methanol, as the relaxation process seems more dominated by the properties of the solid, and that's the information it's giving us, rather than anything necessarily about the solid-liquid interaction strength. So that's a bit of a detailed summary on what we can do with single component adsorption. So the next logical step would be to see what happens when we put multiple components inside these porous media. And we want to know, can we separate out these components? Can we quantify the compositions? And are there any co-adsorption effects that reveal themselves in the NMRD profiles? So we made up a bunch of binary liquid mixtures of THF cyclohexane and methanol THF at a range of different compositions and imbibed them in the alumina pellets. And on the left, we've got at the top the single component distributions, the single component T1 distributions for methanol THF cyclohexane. And at the bottom, we've got the distributions we obtained from the liquid mixtures. And based on the relaxation rates, we were able to separate out these components really quite nicely and identify THF and cyclohexane. And what was also very nice was that we got robust peak integrals across the frequency range. So we're actually able to quantify how much of each of these species exists within the pellet space. And this is not necessarily the same as the amount that we put, it's not necessarily the same as the composition of the liquid in which we imbibed these pellets. You get a similar thing on the right for the methanol THF binary, where you can clearly resolve the different environments, though the OH group was quite small in terms of its population, quite sensitive to noise, and it wasn't as robust as the methanol CH3 group. So for the remainder of this talk, when I talk about methanol, I'm referring to only the CH3 group. So now that we know that we can quantify composition and separate everything out, we had a look at what's happening to the relaxation behavior of these liquids inside the pore space. And on these graphs, we've got plots of the NMRD profiles of each different component in the binary liquid mixture at each of the different compositions. And the arrows represent what happened to the relaxation behavior as the composition of each species in the binary was decreased. So in the THF cyclohexane case, we see that when we decrease the composition of THF in the binary, we increase its relaxation rate. And that's indicative of THF outcompeting cyclohexane for surface binding sites. And what was really interesting was when we took the same THF in the same gamma alumina pellets, but this time we imbibed a more polar methanol species with it. we saw that the THF relaxation rate decreased as the concentration decreased, because now methanol was completely outcompeting THF for surface binding sites. So we can see how fast field cycling can be a really nice tool for studying competitive adsorption of these liquids in porous media. And we wanted to see if we could quantify this further. So what you'll probably notice from these profiles is that although they're shifting up and down a bit, they're not really changing shape much. And if you take each of these profiles and renormalize them by the relaxation rate at 10 kilohertz, you actually end up with something that looks like these figures on the left, where all of the circles and crosses represent each species in the binary liquid mixture, and the solid lines represent the case of single component adsorption. And what you see is that the relaxation behavior of the strongly interacting species is unaffected by the presence of the other component for both binary liquid mixtures. And this is suggestive of a very strong competitive adsorption, and likely a microphase separation where one species is completely dominating the surface and forcing the other away. And to check whether this is what's going on, we can go back to the two-phase fast exchange expression that we introduced a while ago, and I've put up at the top of the slide. And we can treat each component in the mixture as if it were a liquid in a partially filled pore. So an 80-20 cyclohexane THF pore, or mixture in a pore, can be considered as a pore that is 80% full of cyclohexane, and a separate pore that is 20% full of THF. And in this case, we reach the expression that's shown here that describes the relaxation, or the observed relaxation behavior of each component in the binary liquid mixture. And for the more polar species in the binary, we note that this surface volume term is going to be constant at 1 monolayer. So the strongly interacting species is completely dominating, well, in the case of a microphase separation, the strongly interacting species is completely dominating the surface binding sites, and that VS term becomes constant. This pore volume term is a fixed constant because that's a property of the porous medium. And the graphs on the left tell us that for the strongly interacting species, this surface relaxation behavior is constant for a given field strength. And that's constant across the composition range. So if we look at our binaries and we compare 1 over the observed relaxation rate of the strongly interacting species, in the case of a microphase separation, we'd actually expect that to be proportional to 1 over the filling factor, so how much liquid is in the pore. And when you do that, this linear behavior is exactly what you see. So these two graphs on the right represent the strongly interacting, or the more strongly interacting species in both the THF cyclohexane binary and the methanol THF binary. And each line represents a different field strength that we've done this analysis at. And you see that you get this linear behavior at each of these field strengths as predicted by our fairly simple model, which is indicative of a microphase separation occurring. So that means that we can use fast field cycling to not only get dynamical information about these adsorbates in porous media, but we can also use it to start getting structural information about microphase phenomena and liquid structuring within the pore space itself. So I'd like to just end by summarizing quickly and saying that NMR Relaxometry is a very powerful tool for studying adsorption of liquids imbibed within catalytic materials. You can use high field relaxation methods. They can be very effective in certain situations, but not always. And in cases where you need more information, fast field cycling is an excellent complementary technique that can be used to classify, rank, and gain insights into the fundamentals of the adsorption process. And you can extend that analysis to multi-component systems and study liquid co-adsorption and structuring within porous media. And then I'll just finish off by thanking Lynn, Mick, and Andy, my supervisors, and everyone else at the MRRC, Professor Jean-Pierre Korb, who I've had a fantastic collaboration with over the years, funding from the EPSRC, Shell, who now fund my postdoc, and the ICME Andrew Fellowship. And of course, everyone out there for listening. Thank you very much. Are there any questions?